Hi students, Professor Jake Abernathy here again on the 12th floor of Coda. We got Spring Street behind me. I'm going to try something different today, a little surprise for you guys. Doing a lecture with an actual physical whiteboard. What do you think? Nice and clean. Let's do some teaching on it. So today we're going to talk about graphs. In fact, for the next several lectures we're going to discuss graphs. As you already know, a graph, G, is a set of vertices with a set of edges. N typically represents the number of vertices you have in the graph, whereas M represents the number of edges in the graph. So you can have two types of graphs. You can have undirected graphs, where the edges, ij, you have an ij pair in the graph as part of the edge set. That just means that I and j are connected. There's no directionality. It doesn't mean that I points to j or j points to I and j are just connected in this undirected graph. In the directed graph, though, if you have ij in the edge set, that means that I points to j. There's a directed edge from I to j. So there are two ways to represent graphs. So here's a graph with 4 nodes. How can we represent this 4-node directed graph? Well, there's one way to do it, which is to write the connections, the edges in the graph, in the format of adjacency matrix. Here's the adjacency matrix representation. Right? You put a 1 in the first row and second column to represent the fact that node 1 is connected to node 2, and so on and so forth. You put a 0 if there isn't a connection. This is not the most efficient way to represent a graph typically because it requires O of n squared space to store. Another way to do this is using adjacency lists. With an adjacency list, you can simply represent the list of every node's neighbors, right? For every node, in case 1, it's connected to the node 2. Node 2 is connected to nodes 3 and 4. Node 3 doesn't have any nodes that it's pointing to, and node 4 has one node that it's pointing to, the node 1, right? This is a slightly more efficient representation of the graph because it requires on the order of O of n plus m to store the graph in this form. So let's say you're given the adjacency list representation of a graph. How do you explore the graph? How do you search through all of the nodes in this graph? Well, there's basically 2 standard ways to do this. One is called depth first search, and the other one's called breadth first search. So the way to think about depth first search is that you're going to be exploring this graph. You'll be iteratively jumping from neighbor to neighbor, but you're going to add new neighbors to a stack. A stack data structure uses LIFO, that's last in, first out. And LIFO, you pop elements onto the stack and then you pull them off, right? And if the last thing that went on will be the first thing that will get pulled off of this stack. In breadth first search, it's very similar, but you're not going to use a stack, you're going to use a queue. A queue uses FIFO, first in, first out. Recall the way a queue works. You take items, you enqueue them into the back of the queue, and you dequeue them from the front of the queue. So what is DFS going to do? DFS is going to repeatedly try to visit new nodes, mark them as visited, and then immediately go to their neighbors and try to search through their neighbors' adjacency lists to find unvisited nodes. It does this in you can think of it as a recursive fashion, and you can actually implement the stack that you're going to use for DFS in a recursive fashion. So let's say, for example, the first node that DFS looks at is node A. We're going to mark A as visited. A then looks at its adjacency list. It finds B. So we now move on to B. B gets marked as visited. B now looks at its adjacency list. B finds C. C gets marked as visited. We now look at C's adjacency list. We find node D. D is now marked as visited. We look at D's adjacency list. We find H. H gets marked as visited. We now look at H's neighbors, H's adjacency list. Maybe H, we find C as the first node. Unfortunately, C is already visited. We call that a back edge. So you actually ignore it because it's been visited and you move on to the next unvisited node. Let's say, for example, that H looks at its adjacency list and finds K. K gets marked as visited. Now, from K, we find F. F is the next node in K's adjacency list. We mark it as visited. F then finds G as its first node in its adjacency list. It marks it as visited. G then looks at its adjacency list. It finds K, but K has already been visited. So now we're done exploring G. We go back, we're done exploring F. F has no more unvisited neighbors. K again does have an unvisited neighbor. K has an unvisited neighbor L, so we move on to L. L looks at its adjacency list. It finds no more new unvisited nodes in its adjacency list. So we go back to K. K again looks at its adjacency list. It finds no unexplored, no unvisited nodes in its adjacency list. So we go back to H. H looks at its adjacency list, finds no unvisited nodes. It goes back to D. D finds no unvisited nodes at its adjacency list. So we go back to C, and then back to B, and then back to A. Of course, A does find an unvisited node in its adjacency list. It finds node E. So we visit node E, we mark it as visited. E looks at its adjacency list. It finds node I. We mark I as visited. I looks at its adjacency list. It finds node J. We mark J as visited. J has no unvisited nodes in its adjacency list. So we go back to I. I has no unvisited nodes in its adjacency list. We go back to E. E has no unvisited nodes in its adjacency list. We return to A. Now we're done exploring A. Of course, on the outer loop of depth first search, there will be an attempt to visit all nodes in the graph, even nodes that wouldn't have been connected, that you wouldn't have found through the search through A, let's say. So eventually the DFS will loop through all of the nodes, find node M has not been visited. It'll look at all of the neighbors, it'll mark M as visited. It'll look through all of the neighbors of M. It'll find this one node N, which is unvisited. N wasn't visited before, so mark it as visited, but it has no unexplored neighbors. So we go back to M. M again has no unexplored neighbors. So we're done performing the depth first search. Let's actually look at some pseudocode that actually describes this in precise detail. Okay, so now we're going to implement DFS in pseudocode on this nice whiteboard here. We're going to implement the stack data structure using recursion. It's kind of a neat trick. So first, let's define the outer loop. The outer loop here is DFS. What it does initially is it sets a flag, the flag visited for every node to be false. Every node is not yet visited. And then it loops through the nodes again. And if a node has not been visited, it calls the explore v function. It calls explore on the node v. Okay, so what does the explore function do? Explore is going to first set the visited flag to be true, and then it's going to look at all of the neighbors Z that are connected to W. It's going to look at all the neighbors Z that are connected to W. W is the input node. And if that node has not yet been visited, it's going to recursively call the explore function on that node Z. And you'll notice this implements the aggressive depth first search method that I showed you in the last in the last segment. When you have an undirected graph, G, we say that two nodes, V and W, are connected if there's just some path between V and W in the graph. The connected components of a graph are the maximal sets of connected vertices. It's the sets of nodes where all of the nodes in every set are connected by some path. Here's an example. We have an example of a graph. This graph has three connected components. Here is a maximal set of connected vertices. Here is another maximal set of connected vertices. And then there's this isolated node right here, and that is also a maximal set of connected vertices. So there are three connected components in this particular graph. So how do you count the number of connected components in a graph from DFS? Well, it's actually pretty easy. It turns out that the number of connected components in a graph is going to be the number of times that this if condition right here returns true and goes on to the explorer process. Every time you call visited or you call explorer v, this is going to find all of the nodes connected to v, and it'll only return here when it's done. So the number of times that you actually call this this explore function from DFS is going to be exactly the number of connected components in the graph. Okay, so we've done a depth first search, but for undirected graphs. Now let's look at depth first search for directed graphs. I think it's actually a somewhat complicated algorithm to write down in pseudocode, or it requires some extra lines. It's a little bit hard to read the algorithm, but it is easier to see what happens if you just look at the algorithm in practice. DFS for directed graphs is actually going to store more information. First, it's going to build what's called a DFS tree. It's going to sort of store all of a certain set of the edges along the way that it used for exploration. And it's also going to record some clock times. It's going to record the event at which it started exploring a node and when it finished exploring a node. So keep your eye out for that when I run this algorithm. First thing we have to do is pick a root node of this graph. Let's say that the root node is B. So we have node B. B is being explored at the first step of this algorithm. So I'm going to put a 1 right here. And now I can iterate through the neighbors of B. Remember that because this is a directed graph, the neighbors of B are the nodes which B is pointing to, and that would in this case be A and C. But let's start with node A. I've now now visited A, so I'm going to write A down. A is now visited. I'm going to mark it with a 2 because I started exploring it at time 2, and I make sure I include this edge from B to A. Okay, now I'm at node A. I want to explore the neighbors of A, the nodes which A points to. In that case, the nodes that A points to is just D. We have node D, so I write node D down. I mark that with a 3, and I record the edge from A to D. Okay, now we're sitting at node D. We look at the nodes that D points to. The first one in the list that I see is node E, so I'm going to write E down here. I'm going to mark the clock time of when we started exploring it, which is 4. And now, again, I look at E's neighbors. E is pointing to G, so I record G here. I record the edge to G. I started exploring G at time 5. Now we look at G's neighbors. G is actually not pointing to anything, so I have completed exploring G. Because I've finished exploring G, I can record the completion time with a 6 right here. I completed exploring node G at time 6, and what I do is I hop back up my tree. I look at node E, and I try to continue to iterate through the neighbors of E. I already looked at node G. That wasn't the only neighbor of E. E has another neighbor. E has neighbor A. Unfortunately, I've already explored A, so I'm not going to continue to add A as a visited node. It's already been visited. But I am going to record, at least in a dotted line, that there is a back edge from E to A. So there's this little back edge going from E to A, and I just keep track of that. Now I've looked at all of the nodes that A is connected to, all of E's neighbors. So I'm done with exploring E. I'm going to write down the clock time 7 of when I completed exploring E, and now I hop back up this tree to node D. I now continue to iterate through D's neighbors. I already looked at E. Next thing I'll look at is G. You'll notice that D is connected to G, but G has already been visited. So I'm just going to record this edge as a dotted line down to G. But because it's been visited, I continue. Now I look at the rest of D's neighbors. Finally, D has neighbor H. So I draw an H here. H is going to get an 8 because I started exploring it at time 8 in this step 8 of this algorithm. I record that edge. Now I look at H's neighbors. H has only one neighbor, and that's neighbor G. So G has already been explored, so I simply record a dotted line edge that's not going to be included in my tree, but I'm going to store it anyway. I noticed that H has no more neighbors. I've already explored all of H's neighbors, so I've finished the exploration process for H. So I'm going to record the completion time for exploring H with 9. I now pop back up to node D, pop back up the tree. I notice that I've now recorded all of D's neighbors. I've visited all of D. All of D's neighbors are now visited. So I record the completion time of D. I pop back up the tree. I'm now at node A. I noticed that A only had one neighbor, and that was D. So I record the completion time of A as 11. And now I pop back up the tree. I'm now at B. I look at the rest of B's neighbors. So far I'd only looked at A, but notice that now B is also pointing to C. So I include C as a node in this tree. I record the edge connecting from B to C, and I record the clock time of 12, which is when I started exploring C, node C. Now let's iterate through C's neighbors. C has one neighbor, and that's F. So I record the node F. I draw an edge from C to F, and I write 13 down because 13 is when I started exploring F.
F has exactly one neighbor, two neighbors. But first, let's look at H. H has already been recorded, has already been visited. So I'm going to just draw a little dotted line to H. Again, I then look next at F. It's connected to B. Of course, B has already been explored. So I'm just going to record this as a dotted line. Now I'm finished exploring F. I can write 14 is the completion time for exploring F. I pop back up the tree. 15 is the completion time for exploring C. I've now finished exploring C. I pop back up the tree. And 16 is the completion time for exploring node B. I've now explored the entire graph, and I've recorded this tree. You'll notice what I have left here is a tree. There's the root node B, and then there's all of these ancestors, all of these descendants, underneath B. So let's just note a few of the pieces of information that we collected while we were exploring this graph and doing the depth first search. Notice that we wrote down these two numbers. For example, for node C, we started exploring C at 12 and we stopped exploring it at clock time 15. Let's call this first number pre of C and this second number post of C. We're just going to use this terminology, pre of C and post of C, when I started exploring it and when I finished exploring it. Second of all, you'll notice that there were these edges that were dotted lines. They were not used in the tree construction. I didn't use them to construct this tree, but I encountered them along the way, along the DFS, and I didn't include them in my tree construction because they didn't visit new nodes that I had not visited before. So I marked them with dotted lines. Notice that there's three types of these dotted edges here. There are some dotted edges that take you from some node, let's say like going from D to G, right? This edge right here, that takes you from D to one of its descendants, and we're going to call that a forward edge, a forward edge. There are also back edges, like going from E to A, because A is an ancestor of E. Notice that this dotted line here goes from E to A. That's a back edge. We also have these cross edges from F to H. What's a cross edge? Because F is not an ancestor of H, nor is F a descendant of H, we're going to call that a cross edge. It's neither a back edge nor a forward edge. That means it's a cross edge. So just keep in mind these three different types of edges that were not used in the tree, but were explored nonetheless when we ran the DFS. So let's make a cool observation about the pre and post numbers that we recorded, and also the nature of these edges that were not part of the tree, but that were observed along the way. Let's just take, for example, the edge that went from D to G. So this forward edge that goes from D to G, which we found along the way, but again, wasn't part of the tree. You'll notice something interesting. The pre and post for D is 3 and 10, and the pre and post for G is 5 and 6. You'll notice that 3 and 10, that segment contains 5 and 6. And that shouldn't be surprising because we got to D, we then explored a node and finally got to G, we started exploring G, finished exploring G, and then eventually returned back to finish exploring D. You'll notice that that segment, the pre and post of D, completely contain the pre and post of G, right? The pre and post of G are in the interval from the pre and post of D, right? And you get a similar effect for back edges. Let's just look at the back edges from F to B. Notice that we have this back edge from F to B. You'll notice that the pre and post of B completely contain the pre and post of F, right? You have the pre and post of B upper and lower bounding the pre and post of F, right? Because in this case, it's a back edge, so they swap places. Similarly, for a cross edge, when we have this cross edge here, you'll notice that the pre and post of G just don't intersect at all with the pre and post of H, right? You had this cross edge H, and you'll notice that there is simply no intersection between 13 and 14 and 8 to 9, right? There's just no intersection between the pre and post of G and the pre and post of H. And this actually fully characterizes the nature of these dotted edges, right? These special edges that weren't used in the tree. You can look at their pre and post numbers and decide if it's either a back edge, a forward edge, or a cross edge, simply based on which of these three behaviors of their pre and post values are true, right? And it's only going to be one of these three cases. So it's a very nice fact about these dotted edges. Let me just emphasize that the reason we like these properties that determine that characterize what is the type of these dotted edges, it turns out that these properties make it very easy for us to detect efficiently whether an edge is a forward edge, a back edge, or a cross edge. And that's going to be really important when we want to determine if we found a cycle in the graph. So let's now talk about cycles in graphs and graphs that don't have cycles. So let's try to do a quick proof of an important fact. A directed graph G contains a cycle being a sequence of nodes where you can get from one node to the next, and all the way back to the beginning by just following edges. That's a cycle. So this directed graph G contains a cycle if and only if its depth first search finds a back edge, finds some back edge in the process of generating the DFS tree. Let's see if we can prove this fact, or at least give a sketch of the proof of this fact. All right, so let's do one direction of this proof. So if the depth first search algorithm does find a back edge, how do we know that this graph has to have a cycle? Well, let's think about this. Let's say this is the depth first search tree that was generated using DFS. And let's say somehow a back edge was found. In this case, the back edge is going to go from D to A. You'll notice that as soon as you have this back edge, you can already see that the graph is going to have a cycle. The cycle is going to be A to its descendant B to its descendant D, all the way back up to the top node A, right? This back edge produces a cycle because it goes from all the way up to an ancestor of D, and so you can just follow the chain from A to D and then follow the back edge, and suddenly you've produced a cycle. Okay, now the other side of this proof requires you to show that if the graph has a cycle, then the DFS algorithm will produce a back edge. I'm going to leave that one for you guys as an exercise. So let's define this thing called a DAG. It's a very common type of directed graph. A DAG, which just stands for directed acyclic graph. It's just any directed graph that doesn't have any cycles. There can't be any cycles in a DAG. Note, it's always possible to take a DAG and topologically sort it. So what does topologically sort mean? It means that once you order the nodes in a certain order, all of the edges are pointing in the forward direction. So here's an example. You have this, this is a DAG right here. You'll find that there are no cycles if you look carefully at this graph. And once we topologically sort it, we pick an order for the nodes in the graph. In this case, it's going to be A, B, D, C. And you'll notice that all of the edges in this graph are all pointing in this direction, right? All of the edges are going in this direction. So this is a valid topological sort. There are cases where there are multiple topological sorts for a DAG, but as long as there exists one, then you know you have a DAG. And you know that because you can't have cycles in a topologically sorted graph. Why can't you have cycles? Because a cycle would require one of the edges to point backwards. So once it's topologically sorted, you can be sure that you have a DAG. So here's an interesting question. How do you actually produce a topologically sorting of a DAG? That's a good one, and it turns out we have an easy answer now. You just, run DFS, the DFS algorithm on this graph G, and then you simply sort the nodes in the graph according to their post value. This value came out of the DFS algorithm. You sort from high to low, the highest post value first to the lowest post value. So the question is, why does this trick work? And it's pretty easy to see why this is going to work. It only takes a couple of simple observations. One is that when you run DFS on a DAG, because there are no cycles in the DAG, we know that that means that there can't be any back edges. Because this is a DAG, it has no cycles, therefore DFS can produce no back edges. And because of that, every edge that goes from W to V in this graph has to have the following property be true. The post of W is going to be larger than the post of V. The only time that this wasn't the case was for back edges, but we know that there are no back edges, so this property has to hold for this particular graph after we've run the DFS algorithm. So just, you may have to convince yourself that this is true, but this is a nice property that we get from the tools that we built from the last couple of segments.